somebody help, not just anybody help. You know I need someone help.
Okay, this video will cover page 394, number 39 through 51. This is from Unit 3, Bonding, and I'll be going over these questions, and hopefully this will help you guys. Enjoy. Okay, for number 39, it says to write electron configurations for the most stable ion formed by each of the elements, rubidium, barium, selenium, and iodine. And it says when in stable ionic compounds. So these guys are a collection of metals and nonmetals. The first two are metals, so they'll be losing electrons. The second two, selenium and iodine, will be gaining electrons. So I'll show you the rubidium, and we'll do the iodine, which will become iodide when it becomes an ion. So rubidium, we will look at a periodic table here. So we look at rubidium, and rubidium, as you'll notice, is in group 1A. That means it has one valence electron. So when rubidium reacts, because it's a metal and it has one valence electron, it will lose that valence electron. So rubidium ends in 1, 2, 3, 4, 5s1. That is the last portion of that electron configuration normally. However, it's going to lose that one electron, so we'll go to the electron configuration of krypton, which is number 36. Now the question doesn't state whether to give the full electron configuration or the abbreviated electron configuration, so I'm going to show the abbreviated for this one since it's kind of a long one. And we're looking at going to the noble gas configuration of krypton for this guy. So we can start with argon as our first element. So I bracket that guy as AR, and then I just continue in with the rest of the electron configuration. So we have argon, and then we have 4s2. After the calcium, we drop down to 3D, and that'll be 3D10. And after 3D10, we climb back up to 4. It'll be 4p6. So that would be the electron configuration for the rubidium when it's an ion. Okay, and rubidium gets to keep its name because it's a metal. It would have that electron configuration. It still has 37 protons, but now it has 36 electrons, and if you add those guys up, you get an overall charge of 1 positive. So we see rubidium will be a +1, and it can be written like that. We can write it as 1+ if you want. You may see it as +1. I tend to write it like that because it's easy. It saves me valuable milliseconds of my life by not writing the 1. You can do it however you'd like. When we're doing the electron configuration for iodine in its stable ionic state, you have to remember that iodine, as you notice, is in group 7A or family 17. Iodine is number 53, and it has 7 valence electrons. Remember, just look at the Roman numeral. That'll give away the valence electrons. The noble gases have 8, except for helium. Iodine will gain 1 electron because it's got a high nuclear charge for this period. It's second only to xenon. It'll gain 1 electron and attain the noble gas configuration of xenon. So when we do this, we're going to start with krypton. We'll put that in brackets. After that, we jump down to the next period, and we'll have 5s2, then 4d10, and finally we'll end up with 5p6. So iodine normally has, well, it always has 53 protons. It normally has 53 electrons. Its configuration before gaining that electron ended in 5p5. Now it's 5p6. At 5p6, that adds an extra electron, and it now has 54 electrons, giving it an overall charge of 1 negative. So we would write iodine, or I'm sorry, iodide as a -1 charge. And again, you can write it as a 1 negative or just the negative like I do here. When it's 1 charge, it's okay to just leave the number off. Okay, on number 41, this question asks you to predict the empirical formulas of the ionic compounds formed from the following pairs of elements, and then it says name each compound. Well, for starters, an empirical formula is just the lowest whole number ratio formula for a compound. For ionic compounds, they're usually pretty cut and dry because each of those ions has a particular charge or charges. So we'll look at the lithium and the nitrogen first. Lithium is a +1 ion. Nitrogen is a 3 negative ion based on where it's at on the periodic table. So therefore, it's going to take 3 of these guys to cancel out the charge of 1 nitride ion. Remember, the compounds must be balanced in charge, and so we end up with Li3N for that. Okay. If we look at the G, A, and O, that's gallium and oxygen, in this case gallium and oxide, we'll see that it's slightly different. So gallium on the periodic table, if you look on your table, is in family 13 or group 3A. And so gallium has 3 electrons. 3 valence electrons. So gallium, which is a metal, will lose those 3 electrons. We end up with Ga with a 3 plus. Oxygen is a 2 minus. And now we've got a little more complicated problem here. We've got a 3 plus and a 2 minus, and so we have to find a common number between 2 and 3, and that number is 6, as you guys know. So we can drop a 2 there, which would give us an overall charge of 6 positive on the gallium side. And if we put a 3 there, that'll give us an overall charge of 6 negative on the oxide side. And so we end up with a balance in charge that is equal to 0, and we have this formula for those guys. The rubidium and chloride and the barium and sulfide work in pretty much the same way as the other 2 examples I showed you. If you need help on those, come in and see me. Okay, for number 43, it says write electron configurations for the cations and these particular anions for these guys. And you look at Mg with a 2 plus, and if you understand what's going on with Mg, you are starting out with 12 protons, 12 electrons. Mg goes to 2 plus, which means it must have lost 2 electrons, so now it's got 10 electrons, and so 12 minus 10 is a plus 2, or 2 plus charge. So that puts it in the same ballpark as neon as far as electron configuration. So you have 1s2, 2s2, 2p6. That gives us a total of 10 electrons. So with all these guys, when they're ions, you're basically trying to figure out which of the noble gases does its electron configuration match up with. And so you either add or take electrons away until you get to a noble gas. Most of them are just a couple of moves on the periodic table to figure that out, and most of them aren't that bad. So these are really not tough. You just got to remember how to do these from first year chem, and if you struggle with it then, we'll fix it now. So again, if you have trouble on number 43, come in and see me, and I'll try to give you some help. Okay, number 45 is probably one of the tougher ones, but if you just think it through, it's not too bad, okay? But I would say out of all the questions, this one you have to think a little bit. It says, which of the following ions have a noble gas electron configuration? And so we look at our choices for A, and there's only one for each of the letters. You look at iron 2 and iron 3, those are thrown in there, and we have scandium and cobalt, both with a 3 plus charge. Okay, so we look at iron and where it's located. It's right here, number 26. And it says iron 2 and iron 3. Well, if you take iron and you move it 2 spaces, that takes it to the +2 status, which is this guy. You move it there, it takes it to the +3. Well, neither of those guys are noble gases, so the irons are out immediately as far as that goes. So iron and 2 2, and 3 are not noble gas configurations. They're stable in charge, but they don't have a noble gas configuration. Okay, so we look at scandium, which is a 3 plus, and we start here at scandium, and since it's losing electrons, I go back 1, 2, and then up to argon. There's my 3 spot, so scandium 3 plus is. Now, there's 1 per letter here, but I'm going to double check the cobalt just to make sure, and we'll see if that's for sure not 1. So we look at cobalt. Cobalt's a +3. Let me get rid of this mess here so you can see it. And cobalt, we use red here. Cobalt's here. If cobalt loses 3 electrons, it would go 1, 2, 3, which puts it at chromium, which again is not a noble gas. So cobalt's going to be out as well. Okay. So for the rest of those on number 45, you pretty much do the same thing. The answers for those, one of them is Te2 minus. The Te tellurium is going to add 2 electrons because it's a 2 minus. So in that case, it moves forward 1, 2, and we're at xenon, which is noble gas configuration. We'll look at the next one, and the answer for that one, I believe, is ceruleum, which is a +4. Ceruleum's down here, and remember, these guys actually fit right here. So we would have ceruleum losing 4 electrons. That's why it's a +4. So we would go back 1, 2, 3, 4, which puts it at xenon, and therefore it is a noble gas configuration. And the last one is barium. That one's actually one of the easier ones. You start at barium, which is here, and it's a +2. So I would move to the left 2, so it would be 1, 2, and again that one's also the same as xenon. So these just have to think a little bit, figure out if you're going to land on a noble gas. If you don't, then it doesn't have a noble gas configuration. So number 47 brings up the idea of the isoelectronic series. The isoelectronic series were discussed in the notes, but just a refresher. An isoelectronic series are a group of atoms or ions that have the same electron configuration. So let's look at A and show you how to do that one, and you guys can figure out the rest on your own if you haven't already. Sodium is 1s2, 2s2, 2p6, 3s1 based on where it's at on the periodic table. If it goes to the +1, we're going to lose the 3s1, and we end up with a configuration that is the same as the element neon. So we have neon as our electron configuration here. So now we just have to find a negative ion that would have the same number of electrons as the positive ion sodium. So we'll look at fluorine, and we'll see if that one will work. And that's 1s2, 2s2, 2p5. Well, fluorine, when it becomes an ion, gains 1 electron. It gets a -1 charge, which means that that 2p5 will become 2p6, and we have a match. So fluoride, F minus, and sodium, Na+, are in an isoelectronic series with neon. Those are 3 elements in there. There's more. And there's more than one answer for this as well. You could have oxide, you could have nitride. They would all have that same electron configuration as neon. You do the rest for the rest of these guys, pretty much the same operation for all of them. And once you get the pattern down of what they're looking for and how to find them, it's really not too bad. Okay, I skipped 49 because it was asking you to come up with an isoelectronic series for neon, and in 47 we did 2 out of those of that series, so it's a pretty easy question. So let's skip to 51. For each of the following groups, place the atoms or ions in order of decreasing size. So we look at copper, and we've got a copper +1 and a copper 2+. A copper atom is an atom that will lose electrons because it's a metal. When it loses its first electron, it goes to copper plus. That's going to reduce its size a little bit, and then you lose another electron, it's going to reduce it even more. So in order of decreasing size, you'd start off with copper. It would go to copper plus 1, which would be the next biggest, and then copper 2 plus, you would lose the second electron there. And every time you lose an electron, the electrons that are still in there can move closer together. Some space is freed up, and the metals will get smaller as their charge, their positive charge, increases in that case. Okay, for nickel, what do we have here? Nickel, palladium, and platinum. We look at those guys, and it's asking about them. They're all plus 2s, as stated here in the question. Since they're all plus 2s, then basically the biggest would be the one nearest the bottom because it's got the most levels. And so that would be platinum. And then you'd have the next one, and then we'd end it with nickel as the smallest. 51C is a lot like A, except in reverse. You have oxygen going to oxide. Every time oxygen gains an electron, it's going to get bigger, and so it basically, they need to make room for the electrons that are coming in. So you go from oxygen, it gains an electron, it still has 8 protons, but it's going to now have 9 electrons, and those 9 electrons need somewhere to go. So the other ones will make space for them. They spread out and repel. And so for that one, the oxygen would be the smallest, so O2 minus would be the biggest, then O minus, then O, going from largest to smallest.